Today's customers have an increased awareness and commitment to quality and service. This places new demands on dealership technicians who are trying to achieve a high level of customer satisfaction. To assist the technicians in meeting this demand for service excellence, the Ford Parts and Service Division has introduced the Service Technician Specialty Training (STST) program. While developing this improved approach to service training, the technical training staff consulted with the training subcommittee of the National Service Managers Advisory Committee, as well as the District Service Engineers Advisory Committee. The result is a training program that will make available to Ford and Lincoln Mercury technicians the information and skills necessary to fix it right the first time. A full menu of new courses are being developed to fully train technicians in these specialty areas: engine performance, engine repair, suspension and steering, electrical systems, climate control, manual transmission and drivetrain, automatic transmission and drivetrain, brakes, and pre-delivery. Training schedules provided by your district office will announce when courses relating to these specialties will be offered.
Commitment to precision service is no more evident than in the pit of a Ford racing team. Here, every measurement, every adjustment is critical. Mistakes can mean the difference between winning and losing. If any system in the vehicle is ignored, it can cost the team thousands of dollars. People in the racing business demand highly skilled, well-trained technicians to keep these precision vehicles in top condition. The Ford or Lincoln Mercury vehicle made for the street is no different. It's also a precision instrument. And today's customers demand the same highly skilled and well-trained technicians to keep their vehicles in top condition. Thanks in part to the Service Technician Specialty Training Program, the Ford or Lincoln Mercury service technician can be considered among the most highly skilled in the business. Welcome to the STST Automatic Transmission Proficiency Training Program, a series of training courses designed with the help of Ford and Lincoln Mercury service technicians across the country. These training courses make use of video self-study programs like this one, which allow you to study at your own convenience. These self-study programs will provide you with the transmission theory and operation knowledge you'll need to participate in hands-on training. In the hands-on training sessions, you'll learn and practice the latest transmission diagnosis and repair techniques. In short, the courses in the STST Automatic Transmission Training Program will help you diagnose and repair transmission concerns more quickly and efficiently, while still providing a quality repair the first time. This will help keep every Ford and Lincoln Mercury vehicle made for the street performing at its peak, just like the ones made for the race course.
The new generation of the Ford automatic overdrive transmission is the AODE. The AODE transmission first appears in the 1992 Lincoln Town Car and will also appear in the Ford Crown Victoria and Mercury Grand Marquis later in the 92 model year. Major component changes on the AODE include the torque converter, which now features a pressure plate style clutch for mechanical transfer of power in second, third, and fourth gears. The fluid pump, which is now a gear rotor design instead of the AOD gear and crescent design, and the main control body, which now features electronic solenoids and a revised valve setup. Several minor component changes have also been made, including changes to the input shaft, clutch assemblies, and output shaft. A stub shaft has also been added to couple the input shaft to the direct clutch. Like its predecessor, the AODE still features a Ravigno gear set, which produces 4 forward speeds plus reverse. The largest area of change on the AODE is in the control system. The EEC4 processor and a network of sensors, switches, and electronic solenoids has replaced the purely mechanical and hydraulic controls. Driver demands can now be translated electronically to the AODE control system through the shift lever, accelerator pedal, and brake pedal, while engine load and transmission conditions are provided to the control system through a network of sensors and switches. The control center for this system is the EEC4 processor. The processor takes the input information from the sensor network and uses that information to control the solenoids in the AODE control body. These solenoids in turn affect the shift timing, shift feel, and converter clutch operation for the AODE transmission. Now let's take a look at the new control system for the AODE. All major functions of the transmission are now controlled by electronics. The EEC4 processor determines engine load, driver demands, transmission state, and other vehicle conditions through a network of sensors and switches. After processing the information from these inputs, the EEC4 controls the solenoids which affect shifting, line pressure, and torque converter clutch operation. Let's now take a closer look at the AODE transmission control inputs to the EEC4 processor. There are 6 inputs related to engine load or driver demands. First, there is the throttle position or TP sensor. You may be familiar with this sensor since it is part of other electronic transmission control systems. The TP sensor uses a potentiometer to detect the throttle plate opening, which is related to accelerator pedal position. The sensor then sends a related voltage signal to the EEC4 processor. The information from the TP sensor is used for the following AODE functions: shift scheduling, modulated converter clutch control, and EPC solenoid pressure control. Engine-related sensors for the AODE include the mass airflow or MAF sensor mounted on the air cleaner duct. The MAF sensor measures the rate of airflow into the engine. The air charge temperature, or ACT sensor, mounted on the air cleaner, provides information on the temperature of the air entering the engine. The EEC4 processor uses both the MAF and ACT sensor information as part of its engine load calculation. This information affects shift scheduling, converter clutch control, and EPC solenoid pressure. Another input used in the engine load calculation is the profile ignition pickup, or PIP signal. The Electronic Distributorless Ignition System, or EDIS module, receives a cylinder identification signal from the crankshaft sensor, then translates this into a PIP signal. Specifically, this signal relates the engine RPM to the EEC4 processor. The RPM information translated from the CID signal is mainly used in shift and converter clutch scheduling. The engine coolant temperature, or ECT sensor, is another engine-related input to the AODE control system. The ECT sensor uses a thermistor to tell the EEC4 processor the temperature of the engine coolant. This information affects converter clutch control operation. If the engine is too cold, the EEC4 processor will prevent converter clutch application, thus helping prevent engine stall. However, the ECT sensor information is a secondary temperature input to the EEC4 processor. The processor will use the ECT information only when it cannot read an input from the transmission oil temperature sensor, which we'll look at in a moment. The air conditioning compressor clutch also provides an input to the EEC4 processor. When the AC clutch is on, the processor will command a boost in EPC solenoid pressure to compensate for the additional engine load. An input to the AODE control system that is controlled by the driver is the brake on-off or BOO switch. The normally open brake on-off switch is mounted on the brake pedal bracket and closes to tell the EEC4 processor when the brakes are applied. This information is used to disengage the converter clutch when the brakes are applied. Now let's review the AODE control system inputs we've just looked at. The inputs related to vehicle condition external to the transmission include the throttle position or TP sensor, the mass airflow or MAF sensor, the air charge temperature or ACT sensor, the PIP signal from the EDIS module, the engine coolant temperature or ECT sensor, the air conditioning clutch, and the brake on-off or BOO switch. These inputs generally provide information related to engine load or driver demands to the EEC4 processor. Now let's look at the AODE inputs mounted on the transmission, which are all related to transmission operation. The first of these inputs is the manual lever position sensor, or MLPS. The MLPS is controlled by the manual lever when the driver selects a range on the gear shift lever. It uses a step-down resistor network to tell the EEC4 processor the manual lever position of the transmission. This information is used to determine the desired gear range and EPC solenoid pressure. The MLPS also contains the park neutral start switch and the backup lamp circuit. Another transmission-mounted input is the output shaft speed, or OSS sensor. The OSS sensor performs a function similar to the governor on the old AODE, only it does it electronically. Specifically, it tells the EEC4 processor the output speed of the transmission by sensing the rotation of the output shaft ring gear. This transmission speed information is necessary for shift scheduling, converter clutch control, and EPC solenoid pressure regulation in the AODE transmission. Further toward the rear of the AODE is the vehicle speed sensor, or VSS. The signal from the VSS is used as an additional speed input to the EEC4 and may cause upshift schedules to be modified. However, the OSS is the primary transmission speed input. There is one more transmission-mounted input, and that is the transmission oil temperature, or TOT sensor. This sensor is mounted on the main control body in the transmission. Like the ECT sensor, the TOT sensor uses a thermistor, this time to tell the EEC4 processor the temperature of the fluid in the transmission pan. The processor uses this information to determine if a cold start shift schedule is necessary. The processor will also use TOT sensor information to keep the converter clutch disengaged if the transmission temperature is too low. Those are all of the AODE inputs. Before we move on, let's show you one more important component on the AODE transmission, the transmission electrical connector. The transmission connector contains the pins for all of the internal transmission circuits. These include the TOT sensor and all 4 solenoids. We'll look at the transmission connector more in our discussion on diagnostics. The transmission-mounted inputs to the EEC4 processor include the manual lever position sensor, or MLPS, the output shaft speed, or OSS sensor, the transmission oil temperature, or TOT sensor, and the vehicle speed sensor, or VSS, which provides a secondary speed input to the EEC4 processor. Now let's move on to the outputs in the AODE control system. The EEC4 processor controls 4 solenoids as outputs: a modulated converter clutch control, or MCCC solenoid, 2 shift solenoids called SS1 and SS2, and an electronic pressure control, or EPC solenoid. Let's take a look at each type of solenoid in detail. The shift solenoids can only open or close a fluid passage. The modulated converter clutch control, or MCCC solenoid, can vary its output almost infinitely. The MCCC solenoid is pulse width modulated, which means it adjusts its position based on the percentage of duty cycle voltage. The EEC4 processor controls the duty cycle by varying its ground switching. At 0% duty cycle, the MCCC solenoid completely closes the ball valve, blocking the fluid output. With a higher duty cycle percentage, the MCCC solenoid will start to rapidly turn on and off. This now allows some of the fluid pressure to flow to the converter clutch control valve. As the duty cycle percentage gets even higher, the on time of the solenoid gets longer, and the solenoid allows even more pressure to flow to the valve. At 100% duty cycle, the MCCC solenoid valve simply remains fully open and full pressure flows to the converter clutch control valve. We'll explain how this affects the converter clutch itself later. Unlike the MCCC solenoid, the two shift solenoids used in the AODE are simple on-off types. They are mounted together in a special housing which is installed in the main control body. The shift solenoids are always serviced as a complete assembly. In the off position, an internal spring holds the shift solenoid ball valve and armature up. This allows some of the fluid pressure passing the solenoid to bleed off to the sump. Thus, the output of the solenoid is less than the input, and the shift valve fed by the solenoid won't be shifted. When the solenoid is turned on by the EEC4 processor, the armature and ball valve move outward and seal off the path to the sump. This means that full pressure will now flow to the appropriate shift valve. We'll show you how the shift solenoids operate in an overall hydraulic circuit in a moment. The electronic pressure control, or EPC solenoid, is unique in that it uses a spool valve. The EEC4 processor controls the current at the EPC solenoid, which adjusts the spool valve position. When there is no ground at the processor, there is no current flow in the circuit, and internal solenoid pressure holds the valve fully outward. This keeps EPC output pressure at its maximum. However, as the processor varies the ground to allow more current flow through the circuit, internal solenoid pressure is reduced and the valve moves back, reducing solenoid output pressure accordingly. Next, we'll show you how the AODE solenoids affect their respective hydraulic circuits. But first, it's time for a few more review questions. Now it's time to look at some examples of how the solenoids we've shown you affect the hydraulic operation of the AODE. For our first example, let's examine the operation of the shift solenoids during a 1-2 shift. In overdrive range first gear, solenoid 1 is on and solenoid 2 is off. With solenoid 1 on, full pressure flows to the 1-2 shift valve, holding it inward against spring pressure. Solenoid 2 is off, so some of the feed pressure bleeds out the exhaust port, and the 2-3 shift valve is not moved. The position of the 1-2 shift valve causes manual valve pressure to be blocked at the shift valve. However, manual valve pressure does flow to the forward clutch by way of the 3-4 shift and orifice control valves. The forward clutch is the only hydraulically applied friction element in first gear. You'll notice that solenoid 1 pressure also flows to the 3-4 shift valve, but the valve is not moved. That's because it takes the combined pressures from both shift solenoids to overcome the spring force at this valve. To initiate a shift to second gear, the EEC4 processor turns shift solenoid 1 off. Solenoid fluid pressure is now reduced at the 1-2 shift valve, and the valve moves outward. This opens up a passage for manual valve pressure to flow to the intermediate clutch. For a shift from second to third, the EEC4 processor turns solenoid 2 on and leaves solenoid 1 off. Thus, the 1-2 shift valve remains outward and fluid still flows to the intermediate clutch. However, solenoid 2 now allows full pressure to the 2-3 shift valve, moving the valve inward. This causes pressure from a second manual valve passage to flow from the 2-3 shift valve to the direct clutch by way of the 2-3 backout valve. The 2-3 shift gives us a good opportunity to show you how the electronic pressure control solenoid can affect the feel of a shift. If acceleration is light, the EEC4 processor, acting on a signal from the TP sensor, commands higher current flow in the EPC solenoid circuit. This means the pressure output of the EPC solenoid will be low, and the 2-3 backout valve will remain inward. The fluid from the 2-3 shift valve now flows through the E orifice, and engagement at the direct clutch is relatively soft. On the other hand, if acceleration is heavy, The EEC4 processor will reduce the current in the EPC solenoid circuit. As you know from our previous discussion on the EPC solenoid, this will increase the pressure output of the solenoid. The increased pressure shifts the 2-3 backout valve outward, causing the 2-3 shift valve pressure to now flow through the K orifice. The K orifice is less restricted than the E orifice, so direct clutch engagements will be firmer. The EPC solenoid and 2-3 backout valve also help control the feel of a 4-3 downshift in this same way. Now let's go back to the shift solenoids and take a look at the 3-4 shift. For a shift into 4th gear, both shift solenoids are turned on by the EEC4 processor. The combined pressures from both of these solenoids is now enough to shift the 3-4 shift valve. The new valve position now directs manual valve pressure to the outside of the overdrive servo regulator valve, keeping this valve from regulating while it also exhausts overdrive servo release pressure. This allows full pressure to the apply side of the overdrive servo, applying the overdrive band. The new position of the 3-4 shift valve also exhausts forward clutch pressure, allowing the clutch to release. Now, let's look at the modulated converter clutch control solenoid and its effect on the converter apply and release circuits. To keep the converter clutch released, the EEC4 processor commands 0 pulse width in the MCCC solenoid circuit. This keeps the solenoid valve closed, and no pressure can flow to the converter clutch control valve. With the valve fully inward, fluid from the converter pressure limit valve flows freely to the release side of the converter clutch. Clutch apply pressure, meanwhile, must pass through an orifice on its way to the converter. If controlled slip of the converter clutch is desired by the EEC4 processor, but not full apply, the processor allows a higher percentage duty cycle in the MCCC solenoid circuit. The solenoid begins to rapidly pulse on and off, allowing some fluid pressure to flow to the converter clutch control valve. The valve moves enough to let some of the clutch apply fluid flow through an unrestricted path to the apply side of the clutch. The valve also starts to open up an exhaust passage for some of the clutch release fluid. There are varying levels of valve movement, which relate to varying amounts of converter clutch slip. If full clutch apply is needed, the EEC4 processor allows 100% duty cycle in the MCCC solenoid circuit. The solenoid now allows full pressure to the converter clutch control valve. The valve moves fully outward, and all of the clutch release fluid is exhausted. Because full pressure is still flowing to the apply side, the converter clutch is fully applied.
For the 1991 Taurus and Sable, the lockup solenoid operation is the same for the AODE as the torque converter bypass clutch solenoid operation was for the AODE. The solenoid is normally open, allowing solenoid regulator pressure to exhaust to the sump. This keeps the converter clutch control valve in position to maintain pressure on the release side of the converter piston plate so the clutch is not applied. However, when the solenoid is energized, it seals off the exhaust passage for solenoid regulator pressure. Solenoid regulator pressure then moves the converter clutch regulator valve to the left, exhausting the converter clutch release pressure. Converter clutch apply pressure, which is always present, now presses the converter piston plate against the converter cover, applying the converter clutch. This might be called on-off control. The ECA also controls shifting on the AODE by operating 3 shift solenoids. Each shift solenoid is normally open. When the solenoid is de-energized, fluid pressure moves the check ball off its seat, allowing the pressure to flow through the solenoid to the shift valve and other components. But when the ECA energizes the solenoid, the armature moves up and holds the check ball against its seat, blocking fluid pressure. So, no pressure can flow through the solenoid to the shift valve or other components. Now let's take a look at how the shift solenoids operate in a 1-2 shift in overdrive range. In first gear, shift solenoids 1 and 3 are off, and shift solenoid 2 is on. Pressure from solenoid 1 is applied to the 1-2 shift valve. Pressure from solenoid 3 is applied to the forward clutch control valve. No pressure passes through solenoid 2. When the ECA orders a shift to second gear, it turns on solenoid 1. Solenoid 2 remains on and solenoid 3 stays off. With solenoid 1 energized, no pressure is applied to the 1-2 shift valve, and it moves left. This applies pressure to the intermediate clutch shuttle valve, causing it to move to the right. Pressure is now applied to the intermediate clutch by way of the main regulator valve and the 1-2 accumulator. This applies the clutch, causing the shift to second gear. The ECA turns the solenoids on and off in this way to control shifting in all gear ranges.
Now, let's get started with the AODE diagnostic procedures. As with all automatic transmission diagnosis, the first step is careful attention and interpretation of the customer concern. In part, you should seek to answer the following questions. Did the condition occur all at once, or did it build up over a period of time? Does the condition occur in all gear ranges or only certain ones? Did the condition occur after service? The next diagnostic step is to perform the preliminary checks. These checks include checking the fluid level and condition, checking the engine and transmission wiring for noticeably loose, damaged, or disconnected electrical connectors, and checking for possible electrical interference from non-factory add-on equipment, such as cellular phones, CB radios, or items wired into the transmission or EEC4 harness. Next, you should verify the customer's concern. Be sure to record all findings. Back in the shop, you should now look up the customer concern on the diagnostic condition cause charts in the vehicle shop manual. These charts should direct you to the diagnostic routines that must be performed. If the condition cause chart directs you to perform electrical diagnosis along with any other checks, be sure to perform the electrical diagnosis first. This may eliminate the need for you to disassemble the transmission. The first electrical routine the chart asks you to perform is the EEC4 quick test using the Superstar 2 tester. The tester hookups and quick test procedures are explained in the Powertrain Control and Emissions Diagnosis Manual. Be sure to record all codes you receive during the quick test. If there are any engine codes retrieved, have these serviced first. This may take care of the concern. The pinpoint tests for these codes are in the Powertrain Control and Emissions Diagnosis Manual. If you receive any transmission codes during quick testing, go to the 3-digit service code chart in the Powertrain Control and Emissions Diagnosis Manual and perform the related pinpoint test for the code you received. The Powertrain Control Manual contains the pinpoint tests for diagnosing concerns external to the transmission, while the Vehicle Shop Manual contains pinpoint tests for internal transmission concerns. The pinpoint tests in the Vehicle Shop Manual are somewhat different than those for previous electronically controlled transmissions. This is because the new transmission tester, number 007-00085, is used for many of the checks involved. If you are directed to perform electrical diagnosis, your next step is to run a check of the electrical circuits inside the transmission, using the new transmission tester. This will verify if an electrical problem exists in the transmission itself. The instructions for running the transmission bench checks on the transmission tester can be found in the tester instruction booklet, which is included in the tester kit. These checks include such items as a solenoid functional check, solenoid resistance checks, and checks of the TOT and OSS sensors. Perform only those tests related to your particular condition. If the transmission tester reveals no electrical problems in the bench tests, there still may be a problem within the transmission. In this case, you will also perform the engine running or road tests using the tester. There are several tests you can perform both in the service bay and on the road, including EPC solenoid checks, engagement checks, even upshift, downshift, and converter clutch engagement checks where you control the actions using the tester rotary switch and solenoid activation switches. If you found no problems on either the bench or road test, but a problem existed on your earlier road checks, it's likely that the problem is not in the transmission. In this case, you may want to check the engine-related inputs, the processor, and the vehicle wiring. Of course, if the problem did show up on the road, but you can't verify any solenoid or electrical problems, you should go back to the vehicle shop manual conditions cause charts and perform the hydraulic and mechanical diagnosis listed for your concern. Those are the major steps for diagnosing the AODE transmission. Now, let's review the order of these steps. First, carefully interpret the customer concern. Second, perform the preliminary checks. Third, verify the customer's concern. Fourth, check the diagnostic condition cause charts to see what routines must be performed. Fifth, perform the EEC4 quick tests with the Superstar 2 tester. Sixth, have any engine codes serviced. Seventh, perform pinpoint tests for the transmission codes you received. Eighth, perform the bench tests using the transmission tester if you're directed to perform electrical diagnosis. And finally, perform the transmission tester road tests if the bench tests failed to locate a problem. Now that you know the major steps, let's run through a typical AODE diagnosis sequence and take a look at these steps in action. The customer of this town car says that the vehicle accelerates fine up to about 25 miles per hour. Then it gets sluggish and the engine seems to whine. Your interpretation should tell you that this is a possible shift problem. We'll perform the preliminary checks first. After verifying that there is no non-factory add-on equipment, we'll perform the fluid level and condition check. The level looks good, and the color and smell appear to be normal. Next, we'll check the wiring harnesses for disconnected connectors or obvious damage. Everything looks good here, too. So we'll move on and perform a road test to verify the customer concern. In our case, the road test shows that the vehicle shifts from first to second normally, but does not shift to any higher gear. Your next step should be to look up this shift condition in the shop manual diagnostic condition cause charts. On the index for these charts, you'll find the category Some or All Shifts Missing. That looks like the one we want. On the chart for the condition, we see that the possible causes can be either electrical, hydraulic, or mechanical. Remember that you should always perform the electrical routines first. The chart says that the first course of action for our shift concern is to run the EEC4 self-test, or have an engine performance specialist run it. The self-test is covered by the quick tests in the Powertrain Control and Emissions Diagnosis Manual. With all safety steps observed, connect the Superstar 2 tester to the self-test connector. It's located in the engine compartment on the town car. The first quick test you'll need to run is the key-on engine off test. For this test, you must be sure that the engine and transmission are at normal operating temperature. With the engine turned off, set the tester mode switches to the fast code and EEC4 settings. Now turn the tester power on and wait for the 0 display. Next, latch the center button down and turn the key on without starting the engine. The tester will run the self-test. The key-on engine-off test will retrieve both hard fault codes and continuous test memory codes from the EEC4 processor. To view the codes after the self-test is complete, unlatch the center button. Then use the memory scroll arrows to check the codes. The first code you see here is a hard fault code 622. The next code, number 10, is a separator code, which lets you know that the remaining codes are from continuous memory. So the next code you see here is the continuous code 111, which is a passcode. After recording these codes, we must now unlatch the Superstar 2 test button, then perform the engine running quick test. For the engine running test, start the vehicle and warm the engine to normal operating temperature again. Now turn the key off and wait 10 seconds. Next, you must go back to the Superstar 2, latch the center button down, then start the vehicle. You can now view the engine running codes by again unlatching the center button and scrolling using the memory arrows. The engine running test provides hard fault codes only. As you can see, we got only the code 622. If you do receive any additional codes, remember to write them down, because when you use the transmission tester later, some false codes will be set. Now, let's look up the code 622 in the 3-digit service code chart for passenger cars in the Powertrain Control and Emissions Diagnosis Manual. Once you find your code on the service code chart, you'll need to find the pinpoint test that goes along with it. According to the chart, you must begin at pinpoint test TC1 in the Powertrain Control and Emissions Diagnosis Manual. Pinpoint test TC asks you to perform a number of tests to determine if the cause of code 622 is in the processor or the wiring outside the transmission. If these checks fail to find the problem, you will be directed to the vehicle shop manual to see if the concern is inside the transmission. According to the pinpoint tests in the vehicle shop manual, code 622 is diagnosed in pinpoint test A. Pinpoint test step A1 lists several items that must be checked in order to proceed. Many of these items should have been taken care of during your preliminary checks or quick testing. After these have all been checked, move on to test step A2. Test step A2 asks you to make sure the vehicle harness connector is fully seated in the transmission connector and that the vehicle harness terminals are fully seated. If the connector and terminals are okay, you can move on to test step A3. Test step A3 asks you to disconnect the transmission connector and install the transmission tester number 007-00085. Since the connector is hard to see on the vehicle, we'll have to show you this operation on the bench. However, be sure to only remove the connector by depressing the tab and pulling up on the harness. Do not attempt to pry on the connector with a screwdriver. You'll damage the connector and possibly cause future transmission concerns. To install the transmission tester, you'll need to select the AODE pigtail harness and overlay from the tester kit. These items are dedicated exclusively to the AODE. Simply install the large connector of the pigtail to the transmission connector. For the AODE, you'll also need to disconnect the output shaft speed sensor connector and install the small tester pigtail connector to the sensor. The other end of the pigtail harness is installed into the tester itself. However, you may wish to install the universal extension cable from the kit between the pigtail and the tester. This will be especially helpful for routing the tester into the passenger compartment. Now, make sure the gear select switch is in the ohms check position, and then plug the tester power supply line into the vehicle's cigarette lighter. Now the tester is ready for use. When you first plug in the tester power supply, make sure all of the LEDs light up momentarily. This verifies proper tester operation. The first specific test in test step A3 says to perform the shift solenoid functional test, which verifies the electrical operation of the solenoids. To perform this test, simply select bench mode on the tester. Select the desired solenoid on the tester rotary switch and press the click test button. The click may or may not be audible, so be sure to check the related LED next to the solenoid jack. If it's green, the solenoid is okay. If it's red, there is a short to power somewhere in the circuit. If the LED stays off, there is no continuity in the circuit. Shift solenoid 1 appears to be okay. Let's try shift solenoid 2. There is no click at solenoid 2 and the LED is off, so a problem here is likely. According to test step A3, we must now go to test step A5. Test step A5 is a check of the solenoid resistance. To perform the resistance check, move the rotary switch to the ohms check position. Since we know there's a problem at solenoid 2, we'll check it first. Connect the negative lead of a digital volt ohm meter to the SS2 jack on the tester, and the positive lead to the solenoid 2 vehicle power or V-power jack. You can see that the resistance at shift solenoid 2 is infinite. Test step A5 says the resistance should be between 20 and 30 ohms, so we know there is an electrical problem with this solenoid or the internal transmission harness. This condition could either be caused by a loose, disconnected, or open wire at the solenoid, or by the wiring inside the solenoid itself. Pinpoint test steps A6 through A11 will help you determine if the transmission wiring or the solenoid is at fault. That's a typical AODE electronic diagnosis procedure. We emphasize that the major steps we gave you earlier are only a guideline. The actual steps you take will depend on your interpretation of the customer complaint and the results of each test.
All 1993 probe vehicles equipped with an automatic transaxle use a 4EAT type GF electronically controlled automatic transaxle. The basic construction of the 4EAT type GF transaxle is nearly the same as the 4EAT used previously on the probe, with the exception of certain enhancements. One purpose of this video is to acquaint you with these new features and technologies, which result in improved shift feeling, improved drivability, improved fuel economy, reduced noise levels, and improved serviceability. There are two engines available for the 93 probe, a 2-liter dual overhead cam 4-cylinder engine on base models, and a 2.5-liter dual overhead cam V6 on the GT. With the 2.5-liter engine, there are two separate control modules, the Powertrain Control Module, or PCM, and the Transaxle Control Module, or TCM. On the 2-liter engine, the electronic controls for both the engine and the transaxle are integrated into the PCM. Now let's look at some of the new input system components. The AODE off switch is located on the shift lever and is used to lock out the overdrive mode. As a safeguard, the AODE off function is canceled when the ignition switch is turned to the off position. Because the AODE off switch has no detent, the switch button returns to its original position whenever the switch is pressed. The manual lever position, or MLP switch, is located on the top of the transaxle. Its function is to inform the TCM or PCM which transaxle range has been selected. The MLP switch has 5 positions, 1 position each for R, D, 2, and 1, with P and N sharing 1 position. The pulse signal generator, or PSG, is a magnetic pickup generator located above the oil pump toward the rear of the transaxle. It detects the forward-reverse drum speed by counting the 32 projections located on the outside of the drum. The PSG produces AC waveforms that are measured by the TCM in the 2.5-liter or PCM in the 2-liter. The transaxle oil temperature, TOT sensor, is located on the valve body and sends a signal to the control module. In the 2.5-liter engine, the signal goes to the TCM. In the 2-liter engine, it goes to the PCM. In turn, the control module interprets this signal to determine transaxle oil temperature.
The 4F20E electronics control transaxle shifting and forward speeds, torque converter lockup, and line pressure with the use of solenoids. As with other electronic transaxles, transaxle problems could either be electronic or mechanical. The power control module sends the TCM engine operating data such as engine RPM, crankshaft position, and throttle opening speed and angle. The TCM uses this input, plus other data, to activate transaxle solenoids and switches that control shifting and other transaxle operations. Some TCM inputs are based on driver demands, such as throttle position and gear selection. Other inputs are provided by the transaxle itself, including vehicle speed, manual lever position, and transaxle oil temperature. The TCM uses this information to determine when the time is right for a gear shift or torque converter clutch application. The TCM also uses this information to determine the line pressure needed to optimize shift feel. To accomplish these functions, the TCM controls 5 electronic solenoids, 2 for shifting, 1 duty cycle torque converter clutch control, 1 duty cycle line pressure control, and 1 for coasting clutch control. This has been an overview of the 4F20E's electronic system. Now, we'll examine some of its components more closely. The throttle position sensor is a potentiometer mounted on the engine throttle body. It sends a varying voltage signal. The PCM can determine throttle position and the speed at which the throttle is opening or closing. The TCM receives this information from the PCM so it can determine transaxle shifting. An idle switch is integral to the throttle position sensor. This is used to detect a fully closed throttle position. A wide open throttle switch is used to indicate a fully open throttle position. This is an input into the TCM and used for shifting information or secondary information for the PCM should the TP sensor fail. A crankshaft position sensor monitors engine speed. This signal is sent to the PCM, which sends it on to the TCM. The manual lever position switch prevents the engine from starting in any range except P or N, and also sends a manual lever position signal to the TCM. As mentioned previously, the 4F20E is equipped with 2 shift schedules that are driver selected. The normal mode, with the power EAT switch off, provides normal partial throttle upshifts. The power mode, power EAT switch on, provides later upshifts to utilize more engine power. A transaxle oil temperature, TOT sensor, located on the valve body, indicates transaxle oil temperature. By knowing the oil temperature, the TCM can determine the oil's viscosity and adjust transaxle line pressure accordingly for smoother shifts. A speed indicator, the pulse signal generator, is located on the transaxle case. This sends the TCM data on output shaft speed. That information is used as backup to the vehicle speed sensor to determine shift points and TCC engagement.
Next, let's look at some output system components and their functions in relation to the TCM or PCM. We'll start with the solenoids. The 1-2 shift, 2-3 shift, and 3-4 shift solenoids control the line pressure applied to the 1-2, 2-3, and 3-4 shift valves. The shift solenoids are switched on and off by signals from the TCM on the 2.5-liter engine and the PCM on the 2-liter. The torque converter clutch control, or TCCC solenoid, controls the line pressure applied to the torque converter clutch control valve. The TCCC solenoid is switched on and off by signals from the TCM on the 2.5-liter engine or the PCM on the 2-liter. The torque converter clutch solenoid, or TCC solenoid, controls the torque converter clutch control valve. The TCC solenoid valve opens and closes the drain port to control torque converter clutch operation. The torque converter clutch control is based on input signals from the pulse signal generator, throttle position sensor, vehicle speed sensor, and transaxle oil temperature sensor. The TCM or PCM determines lockup
and signals the TCCC solenoid to engage. In addition to the normal lockup, a slip lockup condition is provided to improve drivability and fuel economy. The TCM or PCM can also select the lockup off mode based on engine load. The downshift solenoid controls the line pressure applied to the 3-2 timing valve. The solenoid is switched on and off by electric signals from the TCM or PCM. The OD off indicator flashes on either vehicle whenever a failure is detected. On the 2.5-liter model, diagnostic trouble codes are obtained through the OD off indicator. On the 2-liter model, diagnostic trouble codes are obtained through the malfunction indicator lamp, or MIL. Another new feature of this transaxle is engine torque reduction during shifts for an improved shift feel. This is accomplished by the PCM temporarily lowering engine torque to improve shift feel. This is done by inhibiting fuel injection during upshifting. Therefore, the shock felt when the transaxle upshifts is significantly reduced. On the 2-liter model engine, the torque reduction control is integrated into the PCM. On the 2.5-liter model, torque reduction is accomplished by the TCM communicating with the PCM through a reduced torque signal. The PCM will momentarily cut fuel injection to half of the cylinders during upshift if the following conditions are met. The engine is up to operating temperature, and throttle position is between 4/8 and 6/8. Also, the PCM will momentarily cut fuel injection to all cylinders during upshift if the following conditions are met. The engine is up to operating temperature, and the throttle is between 6/8 and wide open throttle. The TCM collects this input information and then sends operating signals out to control transaxle operation. The TCM activates shift solenoids A and B according to signals from input sensors. The shift solenoids, which are normally open, have a simple on-off operation. When set to on, a drain circuit closes and solenoid pressure is applied to the shift valve. The TCM also controls the line pressure solenoid according to the signal sent from the throttle position sensor, thereby controlling line pressure in response to throttle position. Line pressure is then used to control the pressure regulator valve, which adjusts pump pressure for current driving conditions. The line pressure solenoid is duty cycle controlled. When the solenoid is turned off, a drain circuit is closed. A high percentage of off time will reduce the solenoid drain time. This allows an increased solenoid pressure to work on the pressure regulator, and line pressure will be high. The torque converter clutch, or TCC solenoid, is a duty cycle solenoid controlled by the TCM. A plunger closes the drain circuit during the off time and opens the circuit during the on time of the solenoid. A high percentage of off time will reduce the solenoid drain time, which will increase solenoid pressure. Therefore, the torque converter clutch will not be applied. The coasting clutch solenoid is operated by an on-off signal transmitted by the TCM to provide both coasting clutch control, engine braking, and 3-2 downshift timing control. When the solenoid is energized, the drain port is open, and when it is off, the drain port is closed. When the solenoid is off, solenoid pressure is applied to the face of the coasting clutch control valve, and the coasting clutch is applied. Other outputs include feedback to the powertrain control module to indicate operating conditions and a signal to the OD off lamp on the instrument panel.
When a malfunction has been recorded on a 2-liter model, diagnostic trouble codes can be accessed by connecting a jumper wire between the STI or TEN terminal and the ground terminal of the data link connector or DLC, and turning the ignition switch to the on position. When the ignition switch is turned to the on position, the MIL will illuminate for approximately 3 seconds for a continuity check, and then go out for 2 seconds before starting to display codes. When a malfunction has been recorded on a 2.5-liter model, diagnostic trouble codes can be accessed by connecting a jumper wire between the STI or TAT terminal and the ground terminal of the DLC, and turning the ignition switch to the on position. When the ignition switch is turned to the on position, the OD off indicator will illuminate for approximately 3 seconds for a continuity check, and then go out for 2 seconds before starting to display codes. The OD off indicator for the 2.5-liter or MIL on the 2-liter flash each diagnostic trouble code currently in memory in ascending numerical order. After the last code is indicated, the first code will be repeated. The Superstar 2 tester can also be used to access diagnostic trouble codes. When using the Superstar 2 tester, the new SuperMex adapter will be needed. This new adapter is used for all 1993 probe vehicles, with the exception of the 2-liter MTX, which requires no adapter. New adapters have been designed for using the 4EAT tester on the Escort Tracer and Probe. The 1.8-liter engine Escort Tracer uses adapter 007-00100B, and the 1.9-liter uses 007-00100C. The 2-liter Probe uses adapter 007-00100B, while the 2.5-liter uses adapter 007-00100A. The 4EAT tester will allow diagnosis during road test and pinpoint testing. Testing procedures for the on-off solenoid valves has not changed. There are a number of diagnostic trouble codes, and they are explained in detail in the reference manual. The ones we will discuss here are Code 65 and Code 66. When a diagnostic trouble code of 65 or 66 is received, you should perform the pinpoint test for these codes. Duty cycle solenoid valves will be tested for voltage readings when in operation. The procedures for checking duty cycle solenoid valve voltage is as follows. Install the 4EAT tester using the adapter. Drive the vehicle and verify that the following voltages are observed between the 4EAT tester solenoid pin and ground. When the transaxle is in slip lockup, the TCC should read 5 volts. When the transaxle is in complete lockup, the TCC solenoid should read 0 volts. When the throttle is fully closed, the line pressure solenoid should read 8 volts. When the throttle is fully open, the line pressure solenoid voltage should be 0. If voltages are not within specifications, you will need to measure the solenoid resistance, checking for an open or short. Note that all resistance tests are performed with the ignition in the off position and the 4EAT tester installed. When checking solenoid resistance, measure resistance between the 4EAT tester solenoid pin and ground. The resistance should be between 9 and 18 ohms. If the resistance is not between 9 and 18 ohms, then the solenoid connector at the transaxle must be disconnected to measure the resistance between the solenoid connector and the 4EAT tester solenoid pin. The resistance should be less than 5 ohms. Measure the resistance between the 4EAT tester solenoid pin and all other test pins. The resistance should be greater than 10,000 ohms. If not, you must service each wire in question for a short.
Most electronic problems in the engine or transaxle are diagnosed by using the new generation Star Control Unit, or NGS. This advanced diagnostic scan tool will soon be routinely used throughout the Ford and Lincoln Mercury service community. The NGS has diagnostic capabilities far beyond those of the Superstar 2 or the EEC4 monitor recorder. It actually incorporates some features of the Service Bay Diagnostic System, or SBDS. The NGS consists of a universal control unit, connected to a vehicle interface module. The memory card will be updated annually, so that a single memory card will apply to all Ford and Lincoln Mercury vehicles for each model year. For 1993 only, the memory card will include the data needed to read diagnostic trouble codes in pre-1993 EEC4 and MEX vehicles. The scan tool is equipped with a serial link, so it can be hooked up to a printer. You can print the data stored in the NGS memory or even during testing. The control features of the NGS are quite simple and easy to use. A small screen at the top of the control unit displays information. Directly below that are number keys that you may use to enter data. The menu dial controls the highlight cursor that you will use to select items on the screen. Turning the dial clockwise or counterclockwise will move the highlight cursor up or down. The trigger keys are used to select the item highlighted by the cursor and to start or continue a function. Both trigger keys serve exactly the same functions. You may press either one of them. The cancel keys are used to quit a function. Pressing cancel will deselect a function and can return you to the main menu. As with the trigger keys, you may press either one of the cancel keys. Although the NGS serves the same functions previously served by the Superstar 2, the NGS is not intended to be used merely for pulling trouble codes. The NGS can directly see the same operating information as the TCM. The NGS monitors the incoming information from the various sensors, as well as the TCM's output commands. With practice, an experienced technician will find dozens of useful applications for the NGS's advanced capabilities. Now, let's look at how to hook up and operate the NGS. Connect the adapter for the data link connector to the diagnostic data link on the bottom of the NGS. With the ignition switch turned to off, connect the other end of the adapter to the vehicle's data link connector, located beneath the interior fuse panel. Plug the NGS power cable connector into the vehicle's cigar lighter. Now, turn the ignition switch to the on position. This will activate the NGS. After a brief internal system memory check, the NGS is ready for your vehicle selection. If you can't use the vehicle's cigar lighter, you can power the NGS directly from the vehicle's battery. Plug the power cable connector into the battery power hookup adapter. Connect the red adapter clip to the positive battery post and the black adapter clip to the negative battery post. When you use this method, the NGS will conduct its internal memory system check as soon as the power cable connector is connected to the battery, regardless of the position of the ignition switch. You are now ready to diagnose the Villager's Transaxle system using the NGS. The reference book that accompanies this video includes a chart that explains all of the abbreviations used by the NGS. Most of them are very simple, and you will learn them quickly. When you first see the NGS main menu, the highlight cursor will be on the Vehicle and Engine selection line. Press Trigger, and then follow the prompts until you have selected 93 Villager. Depending on your preference, the NGS can display its readings in either English or metric units. From the main menu, select New Generation Star Setup, and then English Metric Unit Selection. Use the correct number keys to select for temperature, velocity, and pressure measurements. From the main menu, you must now inform the NGS of the type of diagnosis you will be doing. Select Diagnostic Data Link with the highlight cursor and press Trigger. Press Trigger again, and you will be offered two options, Engine and Automatic Transmission. By selecting Automatic Transmission on this menu and pressing Trigger again, you will reach the Function menu. There are three functions available in this menu to help you diagnose transaxle concerns. Selecting the Diagnostic Test Mode Results option will bring up a display of any components in the transaxle system where faults have been detected. If the TCM doesn't detect any faults, a No Failures message will appear. This option essentially pulls the diagnostic trouble codes in the transaxle control system. With the engine running, move the highlight to Data Monitor and Record, and then press Trigger. You will see a menu of components concerned with the transaxle system. By pressing Trigger, you can program the NGS to provide current data on the operation of any component you select. An asterisk appears next to those items you choose. Because there are more components than can fit on one screen, you will need to turn the menu dial clockwise and scroll down to see them all. The The small arrow on the right side of the screen indicates that there are additional items. When you are ready, press the 6 button for Start. The NGS will quickly report the current status of each component you selected. To exit the data monitor function, press Cancel twice. The final option on the function menu is the TCM part number feature. Occasionally, the wrong TCM unit may be installed in a vehicle during maintenance. Such a mismatch can cause serious drivability concerns and can be difficult to detect. This feature will retrieve the part number from memory to ensure a correct match for the vehicle. If at any time the link between the NGS and the vehicle is lost, the message TCM not responding, press cancel will appear. This may indicate a missing or disconnected cable, a key off condition, or a defective NGS or PCM. If this message appears, press cancel and continue. If the message persists, there is a definite failure. Let's look at an example of a technician using the NGS to diagnose a concern in the Villager's Transaxle control system. After selecting the Vehicle and Engine Selection option and pressing Trigger, the technician selects 93 Villager. He chooses Diagnostic Data Link. At the next screen, presses Trigger twice, then selects Automatic Transmission. From the function menu, he needs to select Diagnostic Test Mode results to determine if there are diagnostic trouble codes stored in the memory of the TCM. The NGS display shows him that there is a code 1 present, indicating a fault in the pulse signal generator circuit. The technician refers to the 1993 Mercury Villager Service Manual for the pinpoint test for this diagnostic trouble code. The pinpoint test tells him to select Data Monitor and Record from the function menu, and then to drive the vehicle. While driving, he watches the PSG reading on the NGS screen. This pulse signal generator reading should change according to the driving speed. The technician determines that the PSG reading goes up when the vehicle speed goes up and goes down when the vehicle slows down. The pinpoint test in the service manual tells him that the fault must therefore be in the TCM and that the TCM must be replaced.
The intent of this program was to present general principles that apply to all automatic transmissions and transaxles. So you may wish to consult the Ford Service Training Manual's catalog for publications containing details on specific transmissions. You may review this video and the workbook as much as you like before completing the post-test. The post-test will not be graded. However, you will need to know the material covered in the post-test for hands-on courses in this SDSD curriculum. By being prepared for hands-on training, you'll get the most out of the courses, and you'll be able to diagnose and repair Ford transmissions correctly and more efficiently, keeping all your customers' vehicles operating like those precision Ford racing machines.